In the last video, we finally got to doing energy conservation and saw that as long as you didn't care or you knew for some other reason the trajectory and the time evolution information of the interaction, that there was a very powerful technique that would allow you to solve problems a lot faster. Now here I want to take a look at one particular situation is a combination of both momentum and energy conservation. Those are elastic collisions. In fact, literally the definition of an elastic collision is one where kinetic energy is also conserved. So remember, for any collision, momentum will be conserved across the collision as long as we cleverly isolate our system. Now we are also requiring that the final kinetic energy equal the initial kinetic energy. Now, based on what we know about collisions, that may seem a little silly. After all, if two cars bash into each other, energy sure as heck isn't getting conserved as you're busy churning big piles of sheet metal into accordions. But a physicist takes a broader kind of view of a collision. To a physicist, a collision is any sort of interaction where the objects involved change velocity. So, for instance, we could say have two atoms interact via the electric force. They never physically touch each other at all. And so in a case like this, it is actually perfectly reasonable to demand that the kinetic energy of the system afterwards be the same as before. So what I want to do is take a look at one particular case, and that will be a one-dimensional elastic collision with a stationary target. Now this may sound overly limited. The one dimension, sure, but it's a little sporty to go into 2 or 3D. Stationary target. And stationary target, though, isn't such a big deal. And I'll work a little bit of an example of that in a bit. We can always change our perspective. So if we've got two objects that are moving, we can always imagine being an observer who's running along with one of the objects. So then to us, that one object is seen as stationary. So at worst, we may have to change our perspective to a perspective where one object is seen as stationary, solve the problem, and then at the end go back to the perspective that the problem requires. I'll work a little bit of an example of that going on. So with all that in place, we're just going to say we're acting in one dimension, so everything's happening in a straight line. So let's say that our object that's moving is this mass M1 here, moving at V1 initial, and mass 2 is stationary. V2 initial is 0. Now, for the purposes of the algebra, I'm using implicit signs. So this means I'm going to be assuming mathematically that the objects are heading to the right. If we solve and get negative answers, that's not the end of the world. That means the object is actually going to the left. But, we know that if this is a big heavy thing and it hits a little thing, the little thing's going to go flying and the big thing's going to keep on trucking. So there are at least situations where it will be like this. And I should have probably drawn this one here a little shorter. Even shorter than that. There we go. So it will turn out that if the object that's hitting the stationary object is lighter, then it will bounce off backward. And when you solve, you'll get a negative number. That's not a big deal. That just tells us we're going to the left. So let's look at our two conditions. So P final equals P initial. We can write that as M1 V1 final plus M2 V2 final equals M1 V1 initial. Now keep in mind at the moment we don't know what either of these are. We're trying to solve for them both. So here's one of our equations. But fortunately we've got the statement that's an elastic collision. So that means that we can require that the kinetic energy at the end be equal to the kinetic energy at the beginning. So what's that going to work out to be? Well, 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. And then we only got one object moving at the beginning, so that'll be equal to 1/2 M1 V1 initial squared. All right. Now, what's going to proceed here for a bit is just a bunch of annoying algebra. So just hang with it. I promise I'll have some benefits. So I'll try to keep drawing in blue whenever I'm worried about the momentum equation, and pink whenever I'm worried about the energy equation. So I'll take the momentum equation here and I'm going to rearrange it to put the V1s on one side and the V2s on the other side. So that's going to give me M1 V1 final minus M1 V1 initial equals minus M2 V2 final. And what that gets me is I can group this out. M1 V1 final minus V1 initial equals minus M2 V2 final. Alrighty. Now, how's that going to possibly help us? Well, it turns out with the squares here, we can start to be thinking about quadratics and maybe some factoring. So let's do the same thing anyway. So first thing we can do is we can just times everything through by 2, make those annoying halves go away. So that'll give me a M1 V1 final squared plus M2 V2 final squared equals M1 V1 initial squared. And we're going to do the same game. We're going to put all the V1s on one side, the V2s on the other side. That will give me M1 V1 final squared minus M1 V1 initial squared equals minus M2 V2 final squared. These are starting to look suspiciously similar. So let's take this a little further. We can pull out an M1 here. All right. And now we remember, hey, the difference of two squares. When you factor that, that's going to be the one factor plus the other factor times the first factor minus the second factor. So this is going to work out to be M1 V1 final plus V1 initial V1 final minus V1 initial. If you don't believe me, you can check it by just doing FOIL on this. So first V1 final squared, outer V1 initial squared with a minus sign, check, check, inner plus V1 initial, V1 final, last, minus V1 initial, V1 final. Hey, those last two terms cancel, so it does indeed work. Here, let me slide this down just a little bit to right there. Okay, good. All right, so that will equal minus M2 V2 final squared. All right, now what I do is I remember this result I had earlier. So I can divide the two equations. So I will divide the left-hand side of the pink equation by the left-hand side of the blue equation. M1 V1 final minus V1 initial. And on the right-hand side, minus M2 V2 final. And we get a cancel-palooza. We're We're going to have the M1s cancel here. We're going to have the minus signs here. The M2s cancel. This term with the differences cancel, and we lose 1 power of V2 final there. Now, with what's left, I'll rearrange that so that I have the finals on one side and the initials on the other. So that will give me V1 final minus V2 final equals negative V1 initial. Now, for reasons that utterly escape me, most texts, they find this. If you go through the weeds of the derivation, they get this, but then they just substitute it in and call it a day. And it's really unfortunate because this result is super duper useful and is worth having around. Because what this says is if you have an elastic collision, what's this V1 final minus V2 final? That's the speed at which the objects are pulling apart. This negative V1 initial, since V2 was going at 0 to begin with, that's the, if we drop minus signs here, that's the speed at which the two objects were approaching. So what we get is that the relative speed of recession after collision equals the relative speed of approach before the collision. So I find this a really useful result to have hanging around. And this is because at this point I'm going to just kind of wave my magic wand to come up with the answers. But usually, getting one of these is a little ugly. So once you get the one, you can use this thing to say, oh, hey, if the object coming in, let's say coming in at 100 meters per second, and we find that afterwards object 2 goes flying off at 25, well, then the other one better be doing 75 the other way, right? That's the idea. So anyway, you can take this and you can substitute it back in to our momentum conservation expressions. With sufficient crank churning that I don't think is instructive, so I'll just quote the result, you get that V1 final equals M1 minus M2 over M1 plus M2 times V1 initial. And you get that V2 final equals 2 M1 over M1 plus M2 V1 initial. Alrighty, that's all well and good. But we can at least look at this to think about some extreme cases. So let's say in the first case here, when I was first looking at this, I says we know if this one's huge and it hits a little guy, the little thing's going to go flying and this guy isn't going to slow up much. Let's see how that pops out from here. So if M1 is really big, M1 minus M2 is just a shade under M1, and M1 plus M2 is just a shade over M1. So you get a fraction that's just a shade under 1. So sure enough, the big thing just keeps on trucking. Ends up going just barely slower than it was before. But the object flying off, well, 2M1, M1 plus M2 is just barely bigger than M1 itself. So this is a number just barely under 2. So that other thing just goes flying off. Now what about the other extreme? Let's say that you fired a ping pong ball against, a battle tank or something ridiculously huge like that. Well, that's the other situation. So in that case, if you got basically a battle tank here, you fire a ping pong ball at it, the battle tank isn't going to move worth a hill of beans, right? It's basically no different than a brick wall. And we've seen with a brick wall that you bounce back out at the same speed you come in at. So let's see if we get that. So if M2 is really big, then this is going to be a negative number that's just barely under M2. This is a positive number just barely bigger than M2. So sure enough, this is going to be minus a number just barely under 1 of the speed you had before. In other words, you're basically flying out at the same speed you came in. And then here, M1 would be very tiny. It's the mass of a ping pong ball. So even if you double it, dividing by the mass of basically just the tank, because adding the ping pong ball to the tank isn't going to matter, you got a number that's just barely above 0. So like you'd expect. I mean, the tank does move, but you're probably going to have to get the lasers out to measure it. All right, let's just do a problem with numbers here to maybe make this a little more concrete. So let's say you fired a 100-gram ball, rubber ball. And I say fired like out of an air cannon or something like that. Please do not do this at home. So it's 100 grams, so 0.1 kilograms. Let's say it's going 100 meters per second, and we have it hit a stationary bowling ball. So it's initially going at 0. Let's say the mass of the bowling ball is 5 kilograms. I want to know how fast are both objects going after the collision. All right, so this is a case where we've got a ping pong ball hitting a tank, kinda. It's not quite that extreme. So what we expect, estimating the answer, is that the rubber ball is going to bounce back at not quite, a little under 100 meters per second. It'll be, it won't be like 99.99999 because the masses are too similar. But, if it's less than 80, I'd be really surprised. And then for the bowling ball, we expect that it will end up moving forward. Again, because it's not like a tank versus a ping pong ball. We're probably not going to need the lasers to measure it, but here I'm expecting a few meters a second, something like that. So let's just go and plug it in. So I went ahead and just solved for V1 final. So using what we had before, that's going to be M1 minus M2 over M1 plus M2 times V1 initial. So this will be 0.1 kilograms minus 5 kilograms over 0.1 kilograms plus 5 kilograms times 100 meters per second. That's basically negative 96 meters per second. So we're going to end up going off to the left. Okay, and that kind of squares us what we were expecting. We were expecting to be close to 100. We weren't expecting it to be like 99.999 because the masses were at least in the same zip code as each other. So yeah, that's kind of all making sense. Now, if you wanted to get V2 final, you could certainly just plug into the other equation. Absolutely ain't nothing wrong with that. But I think this is where having that relative speed of approach equals speed of recession thing comes in really handy. You know they were approaching at 100. You know they have to be leaving at 100. So if this is going at 96 to the left, the other one has to be going at 4 to the right. So let's just double check that with the math to see if that is indeed the case. But that reasoning is always solid. And again, this minus sign here is just to deal with here it's separation, here it's approach. All right, so we can rearrange and we get that V2 final equals V1 final plus V1 initial. We had that V1 final was negative 96 meters per second. V1 initial was plus 100 meters per second. So sure enough, we get plus 4 meters per second. So indeed, it did end up going to the right, and compared to the rubber ball, it's not going too terribly fast. Cool. All right, so I promised to do an example to show how we can do this if the objects were actually moving. And so a demo that you can go look up watching some, on a Google search or something, watching some idiot doing it at home, or a trained physics professor, one or the other, is you'll find these demos where someone is dropping either like a basketball or a soccer ball or something like that, and sitting on top of it is a tiny little super ball. And if you've ever watched these demos, what happens is so the basketball and super ball will fall down together and hit the surface of the earth. And then what you notice after they hit the surface of the earth is the super ball goes flying. Again, don't try this yourself, because the problem is that super balls are about the size of your eyeball. I think you see where this is going. I don't want you to put your eye out. Go look online and find somebody who has already recorded the video and enjoy it. All right, so here what's happening is this is actually a bit of a three-way collision, because if you think about it, the thing you're colliding with is the Earth. So what we've got is that the super ball we're going to model as basically being way less massive than the basketball, but by the same token, the basketball is way less massive than the Earth, right? So because in order for these collisions to happen, the objects actually have to squish. There's an interesting point where the basketball has completely flattened out. The super ball is still basically just traipsing right along. And then the basketball starts to expand and start to push the super ball out of the way. So there is a point where right after the collision, it's actually accurate to think of the basketball as going up. So if we said this was V1 initial just before we hit the ground, the basketball, after it hits the earth, this is a ping pong ball versus a tank situation. The speed of the basketball after the collision will be minus V1 initial. So in other words, you're going up at the same speed you went down. But here's the deal. So is the ball. So is the super ball, right? V2 initial here equaled V1 initial. So the super ball was going down at V1 initial. So now what we've got is for this split second here, and here we need to break this into two different perspectives. Physicists usually call these frames. So from the frame of the Earth, in other words, us standing on the surface of the Earth looking at what's happening, at this exact moment, we'll say that the ball is going up at V1, minus V1 initial, whatever. And the super ball is still going down at V2 initial equals equals plus V1 initial. Now, since we only came up with the equations from the perspective of something being stationary, we have to change frames to the frame of the basketball. So now, if you're the basketball, what you're imagining is that you are just sitting still. Boom. And what you're seeing is the super ball coming in on you at 2 times V1 initial. Because these are, it's just like, if you're driving up the road at 100 kilometers an hour and someone else is driving down the road at 100 kilometers an hour, you're approaching each other at 200, right? It's exactly the same logic here. So the basketball says, hey, the super ball is approaching me at 2 times the speed that the basketball was landing on the earth at. All right. So again, we can know how to model this in the frame of the basketball now. In the frame of the basketball, this is basically another case of a ping pong ball against a tank-ish. So the basketball will still be staying there. Still basically 0. I'll put a bit, approximately there. But now the super ball is flying up at a shade under our minus 2v1 initial. Okay, so now with that, we can go ahead and shift perspective one more time. So first, we shifted perspective going from Earth to basketball so we could think about the collision in the frame of the basketball. And now we're going to shift back to the perspective of an observer on the Earth. So the observer on the Earth is saying, hey, this is going up at minus v1 initial, right? And we know, looking over here, this is leaving at 2v1 initial versus this. So in order to maintain that rate of separation, this has to be flying up at v2 to an observer as on the surface of the Earth as being about negative 3 v1 initial. So in other words, it flies up at about triple the speed. A little under because the Earth will carry an almost negligible amount of speed away. The basketball will recoil a little bit, so it won't be as good as 3. Maybe it's 2.9 or something like that. But if we just use 3 for nice round numbers here, the kinetic energy of the super ball is now not 3 times, but since it's 1/2 mv squared, it's 9 times what it was just before it hit the surface of the Earth. So that means it's going to fly up 9 times higher than what it dropped from. And like I say, it won't be quite 9. And what happens, the basketball won't go up quite as high as it did before. But yeah, that little super ball is going to go flying. Check out the YouTube videos of crazy idiots and or trained physics professors doing this demo. I think you'll get a good laugh out of some of them. All right. So this is all well and good, but I want to show one application of this that does actually get used all the time. The official name is gravitational assist, which is kind of boring. Some people call it the slingshot effect, and so we'll go with that. So here's the issue. The issue is, how do you get a satellite out to the outer planets? And there's 2 different strategies that you can do to achieve this. The issue here is that a huge percentage of over 90% typically of the mass of a rocket is fuel. The payload is usually only a couple, 3-4%, something like that. And then there's mass of vehicle involved too. So, because the issue is you need fuel to lift the payload, but then you need fuel to lift that fuel, and you need fuel to lift that fuel. I think you see where this is going. So you need an awful lot of fuel to get the rocket going. And to get it to leave the Earth, you've got to get it moving pretty darn quick. Just to get it to leave the Earth and never come back, if you're leaving from the surface of the Earth, you'd have to be going at 11.2 kilometers per second. Now, it turns out to be not quite that bad because the rocket is gaining altitude while it's picking up speed, And as you gain altitude, this escape velocity, it's called, drops to be less than 11.2 kilometers per second, but still, it's a lot. You've really got to be hauling. So you leave the Earth. Now, let's say you're trying to send a probe out to Pluto, or let's say you're trying to do the grand tour of the planets like the Voyager satellites did. There are two strategies you can do. One is you can do what they did with the Voyager satellites. After the cancellation of the Apollo program, they happen to have a couple of spare Saturn V rockets kind of just lying around. So you could go ahead and take the most powerful rocket humanity ever made that was designed to get 3 people, a lunar landing vehicle, a moon buggy, life support systems, you name it, to the moon. That's an awful lot of weight. Now, if you decide that you instead want to move a satellite that's like only the mass of a minivan or something like that, you can strap it onto one of these bad boys and just shoot it out. But it turns out that even with all of the kinetic energy that you could possibly pick up from burning that rocket, that satellite could make it just to Jupiter. This is because as you go away from the sun, the gravitational potential energy is increasing, and so the kinetic energy is decreasing. So here's the thing. When the satellite gets just barely, makes it over to, say, Jupiter or something like that, they'll do a very carefully orchestrated flyby of the planet. So say you're coming in at V1 initial here, and we'll say that the planet is moving at V planet. And you'll just whip around like that. And then the satellite will go flying away. This counts as an elastic collision. Velocities were changed. And so following exactly the same kind of logic you have before, you'll pick up roughly 2 times the speed of the planet. Now you do slow the planet down, basically almost completely undetectably. Someone for funsies did the calculation with the Voyager satellite flying past Jupiter and worked out that in the 5 billion years or so that Earth has left before the sun turns into a red giant and gets big enough to swallow us up completely, we changed the distance traveled by Jupiter by something like the width of a hydrogen atom or something silly like that. It wasn't a whole lot. So you do technically slow down the planet, but not enough that you're ever going to notice. And this kind of thing is happening all the time as comets fly by objects and stuff like that. So it's not just us. But you pick up this boost that can be as much as 2 times the speed of the planet. Now, it's not going to be as good as this extreme case, but it's still pretty darn good. And since the planet is kind of hauling, that gives you a big enough boost that you now have enough kinetic energy to make it out, say, from Jupiter to Saturn. And then if you're on a grand tour, you'll do a gravitational assist at Saturn. So you have to calculate these trajectories very, very precisely. But it can be done, and they know. And so when Voyager was launched, they realized they happened to have just a perfect alignment of planets so that they could fly a satellite past all 4 of the outer planets. So that's how you do it if you have the biggest rocket ever made, which we can't even make anymore for a whole bunch of different reasons. If you're interested in that, check out, say, some of Scott Manley's videos on that. It's kind of interesting. But anyway, how do we do it now? Well, it turns out it's the same trick. The The issue is to get going, again, to get going fast enough to make it to Jupiter. Once you make it to Jupiter, you can get a gravitational assist off of Jupiter to go wherever it is you want to go. But the trick is getting to Jupiter. So nowadays, with much smaller launch vehicles, what you'll do is you'll decide that you're going to spend many, many more years in space. And so, say if you're sending a probe out to Pluto or something like that, the very first place you might launch the rocket to might be Venus. And what you do is you pick up a gravitational assist off of Venus, pick up a little bit of speed. And then if you did it all right, maybe it flies by the Earth, picks up an assist off of the Earth, and maybe back off of Venus or Mercury, and then maybe off of Mars. And you just rattle around back and forth inside the inner solar system until you're finally going fast enough that you can get across the asteroid belt and make it over to Jupiter. There's a pretty big gap of distance between Mars and Jupiter. And by the way, the asteroid belt basically has almost nothing to hit in there. I mean, of course, you will go ahead and have your computers calculate it all anyway, because it would be very embarrassing, but it certainly wasn't like The Empire Strikes Back. In fact, almost the exact opposite. Alrighty, so that is Elastic Collisions. Have fun, and I'll catch you in the next series of videos. Later.